This is Geometry, Chapter 7, Section 5, in which we will study parts of similar triangles. The idea here is we've already found similar triangles. We know how to determine if we have similar triangles. We know how to get the ratios that show the scale factor between similar triangles. So the idea here is if we talk about these special segments that we had, such as altitudes, such as angle bisectors, and such as medians, those things will be in the same ratio as the scale factor is, the same corresponding sides ratio. And we have three separate theorems, one for each of the special segments that goes with triangles. So if our triangles are similar, then the altitudes are proportional to the lengths of the corresponding sides. Angle bisectors are proportional in 7-9, and medians are proportional in 7-10. The three theorems basically say the same thing. It's just talking about different segments, different special segments that go on with triangles. So let's say our job is to find the value for D there. Okay, we're looking at an altitude. I know my triangles are similar because angle K matches angle X. Angle L is equal to angle Z, so I've got angle. And that's good enough to say that the triangles are similar. Well, since the triangles are similar, I can write ratios. The ratio of side in the first triangle to a side in the second, 20 to 15, will be equal to the ratio of the altitudes, 16 to D. From here, it's an easy problem. Cross multiply and then solve, and we find out that the altitude of the second triangle, the smaller triangle, has a length of 12. The same idea would have applied if we did a median or if we did an angle bisector. Now, speaking of angle bisectors, there's a separate theorem that involves just angle bisectors. If we draw an angle bisector in a triangle, then what we get is we have two segments over here, KM and ML, that are in the same ratio as the lengths of the two sides over here, JK and JL. So what this theorem tells us is KM to LM is the same as KJ to LJ. This only works now when we're talking about an angle bisector. It doesn't hold for altitudes or medians, strictly angle bisectors. That's the only option you have for this one. So let's apply this theorem a couple of times. We have an angle bisector drawn in here. We can tell that because they marked the two angles congruent. So we can write ratios. The ratio of these two segments, 4 to 6, will be the same as the ratio of the legs over here, X to 13. I shouldn't say legs, we don't know that that's the right triangle. The ratio of the sides, we use that term. So 4 is to 6 as X is to 13. Now we can write our cross multiply and write an equation to work with. 6x is equal to 52, and then dividing by 6 gives us that our side length over here is 8 2/3. Okay, here's another interesting one. We have another angle bisector. We can tell because they're marked as congruent. So I know these two segments down here on this third side will be in the same ratio as these two. If I know the whole side length is 20, and this part is X, I need some expression to represent this part. Well, if the whole thing's 20 and this part is x, then this part should be 20 minus x. Now I can write ratios. 20 minus x over x is the same as 11 over 14. The ratio of the two segments of the third side here is equal to the ratio of the two sides. Well, now it's an easy problem. Cross multiply. I'm going to distribute, bring the 14x over, and then divide by 25 to find out that x is 11.2. If I needed to, I could now find this other piece over here. We could find that out easily enough. 20 minus 11.2 is 8.8 if we needed that. So not a whole lot here. Remember that the ratios of the corresponding sides is equal to the ratio of the angle bisectors, or the altitudes, or the medians. And then in the special case of angle bisectors, the ratio of the two segments of the third side is equal to the ratio of the two sides that are involved. If you had questions along the way, hopefully you wrote those down. Bring them in with you, and we will see you in class.